So in the previous video, we solved Griffiths Introduction to Quantum Mechanics problem 2.26 as it appears in the third edition of the book. And we solved it by using a brute force method. That is, just not thinking much about it and just going straight into the problem and solving the potential. This time around, we are going to solve the same problem, but using a trick that will make everything a lot easier. So the trick is the one that I proved 2 videos ago, which is that if we have an even potential, right, then we can write the solutions to the Schrödinger equation as the sum of the even solutions, which we can write, which I named psi plus the odd solutions that I named psi minus. So that is what we're going to use. And if you have never used it before, you might be wondering why is this useful at all, but it will be apparent quite soon, so don't worry. So the first thing that we are asked, they tell us, okay, consider this double delta function potential, which is just a double delta well. And as we can see, there's going to be one well at minus a and one well at a. So first we want to sketch this potential. So let's just draw our axes, the potential, and x. So, well, first of all, we are going to have to, at some point, check that this potential is even. You can just go ahead and change x by minus x, and you will see that it's going to be the same as this. And also now, when we sketch it, we can also see that it is going to be even. So at minus a and a, there's going to be these wells. So you can actually see right away that this does look even, and it is. So this is the sketch. It is quite simple. Just make sure to know what's going on, draw your wells at the correct places, and that's about it. So there's not much more to it. So now we want to go to part B, which is to determine how many bound states there are. So remember, first, bound states means energy less than 0. Okay, so how many states have energy less than 0? Well, let's go and solve the Schrödinger equation for our wave function everywhere. So let us, just as we did in the previous cases, name all of our regions. It's going to be region 1, region 2, and region 3. So now with these 3 regions, we have to solve the Schrödinger equation, but notice that the potential is going to be 0 at each of those regions. So it's actually going to be the same equation for all 3 regions, just as it was in the previous video. So what we have to solve there is just going to be minus h bar squared divided by 2m d squared psi dx squared equals to e psi. This is a function of x, obviously, but I'm leaving the of x out for now, as I've done previously, just for simplicity. So how is this solved? This is solved as we have done many times before. We isolate the second derivative and we get minus 2m e divided by h bar squared psi. And since the energy is negative, we have to define k squared, well, or k, as the square root of minus 2m e divided by h bar squared, so that when we take e as a negative number, it's going to be something positive in here. So this is going to be k squared psi. And well, this differential equation we have solved many times. You have to factor out this so that you get it's going to be plus k and d dx minus k times psi equals 0. So we just put this to the left hand side, factor this out, and now we got these 2 separate differential equations which have to be 0 separately. So that way we can find the solutions. We have done this quite a few times before, that's why I'm kind of rushing through this. If you have never seen it, I do recommend you going back and seeing those videos first, because it is a differential equation that you have to know how to solve, because it really comes it appears very often. So the solution to it is going to be some constant e to the kx plus some other constant e to the minus kx. Now remember, this is valid for all 3 regions. So we are going to want to write this 3 times. So psi 1 is going to be that, psi 2 is going to be the same but with different constants, plus d e to the minus kx, and for region 3 we're going to get ekx plus f e to the minus kx. So these are our mathematical solutions. Now we have to look at this and determine which are our physically acceptable solutions. So in the negative region, so if region 1 is when x is less than minus a. So basically x will be negative here. So if we go to minus infinity, this term right here goes to infinity. And remember, we need it to go to 0. So this, then b has to be 0 because that is just not an acceptable wave function. Similarly, for region 3, when x goes to infinity, this term right here will also go into infinity. It's not going to go to 0, so this would not be a normalizable state. So this is just not acceptable. So we take that term to be 0. It's not a valid physical solution. So we are left with this, which is actually the same that we got in the brute force method. So far it's the same. Now comes the difference. So in the brute force method, now we said, okay, let's apply all boundary conditions and just determine all of these constants. But now we are going to use what we saw before. So we know that this is just going to be psi, right, which is divided into these 3 regions. So we can now say, okay, so psi is going to be the sum of some even functions plus some odd functions. So we have to go through each of those 2 cases and see them separately. So what about these psi, right? What about these positive, these even solutions? So let's take a look at the even solutions. So psi plus this right here. So we're going to take psi, but how can we make this even? And this is the thing, since it is a trick, that is why I also think it's good to know the brute force method, because this does require you to think about it. And if you don't really understand it well, it might be difficult, but what we have to do is make sure that this is even. So we have to find some function of x that when we evaluate it at minus x, we get the same thing. So now this does take a little bit of knowing how it works, but you will get used to it if you do it a few times. So the first region is a e to the kx. And what is the first region? It is whenever x is less or equal to minus a. Then we have this second region right here, which is c e to the kx. I've not yet changed anything. I'm just writing it down, and we will change it after I have it here. And this is for x between minus a and a. And then we have f e to the minus kx for x greater or equal than a. So how can we make this even? So first of all, remember, we need this psi plus of x to be equal as psi plus of minus x. That's what it means. So let's say that maybe a is 1, so it's these deltas will be at 1 and minus 1. So let's take a look at what happens outside of these. So basically in regions 1 and 3. So let's say that x is, for example, 2. Just to give a number, right? So we want to see if this holds, or how can we make it hold. So we want psi plus of 2 to be the same as psi plus or minus. So you could do it with some arbitrary number, but I just want this concept to be clear. So that means that in this region, we have to take this part right here. So we would have f e to the minus 2k, and then in this other region, which is going to be region 1, we are going to get a e to the minus 2k, because we have to evaluate it at minus 2. So actually we have the same exponentials, but the constants are different. So if we take f to be equal to a, or a to be equal to f, it's the same, right? We would have the same thing. So now we actually find our first condition for this, or how to make this into an even function. We have to see a has to be equal to f. And if you did, or you saw the previous video where we did this with the brute force method, this is actually one of the things that we found using a lot of algebra, and it was very, very annoying to do. But now, just by analyzing this problem, we already found one of the conditions that we had to get by using, as I said, the border conditions and using a lot of algebra. So this is one condition. Now let us take a look at the region 2, which is between the 2 potentials. So let's say now that we are between this minus a and a. And just so that I can use whole numbers, let's say that a is like 2 or something. So it's between -2 and 2. So let us now evaluate our functions here between just, let's say 1. So we're going to get 1 here, so this will be -1. So we want this function of 1 to be the same as this function of -1. So now what does that mean? That means that c e to the k plus d e to the minus k. Now I just evaluated this at 1. Now let's evaluate it at -1. It would have to be the same as c e to the minus k plus d e to the k. Now, how can we make these two things be the same? Well, if c is equal to d, then we would have, well, let's just replace it. So now, see, we have c e to the k, c e to the k, c e to the minus k, c e to the minus k. So if c is equal to d, then we have that this is also going to be even in the second region. So now our function is even everywhere. So let's just write it in here. You can also just factor out the c here. It's the same. So now these are our even solutions. So, and once again, if you recall what we did in the previous video, we also found this condition, but using the boundary conditions and a lot of algebra. So this is now our starting point. We now want to see how many bound states there are for the case of these even, I don't know why I erased this, to be honest. I'm going to go to the next page anyways. For the case of these even solutions. So let's now take this to the next page. There we go. So now we want to determine how many bound states there are. So as we have done before, let's just apply our border conditions. Now you will notice that in this case, because it is symmetrical, you're going to get the same information for the border between 1 and 2 or for 2 and 3, right? Regions 1 and 2 or 2 and 3. So you can choose either. If you choose both, you're just going to get repeated equations. So it's not going to give you any additional information. And that is because we have already applied these conditions that actually comes from using them both. So we only have to deal with one now. So from the continuity condition, let's say between this potential at -a, so that means that the first wave function, this right here, from this first region, evaluated at -a, has to be continuous throughout this potential. So it's going to have to be the same as this wave function in the second region evaluated at -a. So what that means is a e to the minus ka has to be equal to c factor of e minus ka plus e to the ka. So this is going to be equation number 1. And now the second equation comes from this continuity of the derivative across the potential. This comes from integrating the Schrödinger equation, because we have to find an expression for deep psi dx, but I have done it already, I think at least 2 times in previous videos, so I'm just going to skip it because I'm going to assume that you have watched it. If you haven't and you don't know where this comes from, just go back a few videos in the playlist and you can see it right there. Okay, so what is this condition? That means that the psi evaluated at the second region, right? This is going to be evaluated at -a. It's actually epsilon minus a, but when epsilon goes to 0, it's going to be the same. So it's going to be just evaluated at -a minus deep psi 1 dx evaluated at -a, and this has to be equal to -2m alpha h bar squared times the wave function, either one of them, evaluated at -a. But it doesn't matter which one because they are the same because of this continuity. Okay, so now let's take this to the next page so that we can go ahead and use this. I need to erase this parenthesis. It was not supposed to come with it. Okay, so let's replace all of these things. So taking the derivative of the second part, we are going to get k times c factor of e to the kx minus e to the minus kx. And then we have to subtract k a e to the kx. Was it kx or minus kx? Let me take a look. It was positive kx, right? So it was ka e to kx, and this is kc there's a minus sign that comes from taking this derivative, so I think it's all good. Okay, and then we have this is going to be equal to minus 2m alpha h bar squared, and now we have to take the evaluate this function at minus a. But now what I want to do is, you can obviously take either. Now I know which one to take, but I'm just going to naively take any. I'm just going to say, okay, this a is easier, so I'm just going to write it as a e to the minus k a. Oh, by the way, I haven't evaluated these things yet. I should do that. So this is going to be minus ka, this is going to be plus ka. That's why it looked somewhat weird. And then here we get minus ka. Okay, so now let's bring everything together. So we can start by dividing by this k. So we can write it down here in the denominator. And then we got this a e to the minus ka here and here. So let us actually put all of that to the right hand side so that this equation can look a bit better. So we get c e to the minus ka minus e to the ka is going to be equal to a e to the minus ka factor of 1 minus 2m alpha h bar squared k. So this is actually our second equation now. We have our system of equations that we have to solve. That's a terrible circle. Okay, so I'm going to take both of the equations to this next page so that we can solve them and keep them in sight. So this is equation 1. So now, if you have done the brute force method, you might actually already recognize this. Okay. So now we have to solve this system of equations. You can choose whatever method you like. I think that at least what I like the most is just to put this, take e to the minus ka and write it in here. So when we do that, what we get is, well, this left hand side is going to be exactly the same. And then we have to take this right here and multiply it by what we already had. I'm going to write it down because it's kind of a little bit slanted. So it's going to be 1 minus 2m alpha h bar squared k. So now we can just multiply through. The constant c will cancel out here, so that's we can just leave it out. So now we multiply. So we get this times 1 is e to the minus ka. Then we have minus e to the minus ka factor of 2m alpha h bar squared k. Then we have e to the ka minus 2m alpha h bar squared k e to the ka. So what can we do here? First, notice that it's going to be this term right here is going to cancel out this right here. And now we're going to want to put some of our factors together. So let's just write this a little bit better like this. I'm going to get rid of this parentheses just so that it's a bit cleaner notation. So now we're going to want to isolate our exponentials just as we did in the previous case. So wait, I think I'm missing a sign here, this plus. Yes, okay, I was missing that plus sign, something was off. Okay, so now see, we have one of these to the left, one of these to the right. So it will actually be quite intuitive to just put them together and take this to the left hand side. So when we do that, we get e to the minus ka factor of 2m alpha h bar squared k, and this is going to be equal to 2 times e ka, and then we have minus 2m alpha h bar squared k e to the ka. So notice now I'm going to get rid of this line. We have 2 everywhere, so let's just divide by 2. And now we have this e to the ka. So we can actually just factor out. So we get e to the ka 1 minus this right here, and we can just leave this out. And now the next thing to do would be to multiply through times e to the minus ka, so that we get rid of this exponential. So we get here e to the minus 2ka. And now the final thing to do, but I'm going to do it in the next page. I feel like I'm already erasing too many things, so I don't want to push it. So moving this. Now the next thing to do is we want to isolate this exponential, because remember this equation is going to have to be solved by graphical methods. So let's go ahead and do that. So we have to find some way to write this in an easier way so that we can graph it. So let's multiply by h squared k divided by m alpha. So when we do that, we isolate this exponential because we know how to graph exponentials. And when we multiply this this side through, we get h bar squared k divided by m alpha minus 1. So actually this is a lot easier to graph than what we had before, because this is just an exponential, this is just a straight line, right? So let us go ahead and graph it so that we can see what the solutions are, or at least how many solutions there are. So let us now graph our functions of k in terms of k. Remember, k is related to the energy. So k, the lowest boundary is going to be 0. Obviously it can't actually reach 0, because that would mean it has 0 energy, and that would mean it's perfectly localized and all that, and that's not acceptable. But just for graphing, let's see what happens when k goes to 0. So with this function e to the minus 2ka, it's going to begin at 1. Let's write it over here. And then it's just going to decrease exponentially. So it's just going to be something along those lines. Not the best graph, but we are just sketching, so it's fine. And then we have this straight line. Remember, k is our variable, and this right here is just some constant that depends on the potential itself. So this is going to be a straight line that begins when k is pretty close to 0. It's going to begin from -1, and then it's going to just go straight up. So there's going to be one unique value for energy that satisfies this equation. So that means there's only one bound state. Now, how can we determine the energy of this bound state? First, we need to be given some alpha, and then you are going to have to apply some sort of numerical or graphical method to determine the solution. So because it's not all that it is to determine. So that's why we are going to leave it at this, but this is the way the solution is, and we have already shown that there is only one bound state for even solutions. Now we have to repeat this process for odd solutions. So now come odd solutions. So in this case, let us just go back to our original wave function here. So now we want to build some sort of odd solution. Remember, odd means that our wave function evaluated at x has to be minus our wave function evaluated at, wait, I have too many minuses, minus x. Okay, there we go. Because it's psi minus is just the name of the function. So, okay. So how do we do that? We can do it exactly in the same way as we did previously. Just take a few numbers in each region, just a few values, and see how our wave function has to be. And when you do that, you can actually show, and as we will do, it's just quite simple, that we can leave this first one be. That's for x less or equal to minus a. But the third region now has to be minus a e to the minus kx. This is for x greater or equal to a. Because now if we are, for example, let's say that a is 2, for example, then if we take 3, which means that we're going to be in regions 1 and 3, when we take 3 and minus 3, we're going to get here a e to the minus 3k, and here we're going to have minus a e to the minus 3k. So we're going to have the same, but with a minus, which is exactly what we want with odd solutions. Now for region number 2, with the exact same logic, we're going to get just that C is going to have to be equal to minus D, or D is going to be equal to minus C, but it's the same. So factor of E kx minus E minus kx. And you can see this is also just an odd function. Okay, so these are our solutions. I did go a bit faster because I showed you how you can check it in the previous part. So I want to now continue and not drag this video for too long. So we have to now apply the border conditions. First, the wave functions at minus a have to be continuous. That means a e to the minus ka has to be the same as c e to the minus ka minus e to the ka. And now we know about the discontinuity of the derivatives. That means that this derivative evaluated at minus a minus this derivative right here has to be equal to minus 2m alpha divided by h bar squared times the function evaluated at minus a. Once again, we have shown many times where that comes from, so I'm just going to use it at this point. So doing that, we get this k that comes down times c e to the minus ka. This minus will become a plus because when we take the derivative, this minus comes down and cancels it. So we get plus e to the, and now because we evaluate at minus a, this minus up here will now be a plus, so we get ka. And now we have to subtract this right here. So it's going to be minus ka e to the minus ka. And this has to be equal to minus 2m alpha divided by h bar squared times our wave function evaluated at minus a. Oh, sorry, we are, no, yeah, that's what I wanted to mention. Just as in the same case, we can either pick minus a or a as our boundary conditions. Remember, you will get exactly the same results. In this odd case, you might have this minus sign, but the information given is going to be the same. So it doesn't really matter if you pick a or minus a. You will get to the same results. Okay, so as before, we can now just divide through by k. So we write it down here. And well, actually, let me also write explicitly psi of minus a. So psi of minus a is going to be this right here. So a e to the minus ka. So we can also then put this to the right hand side. So we get c factor of e to the minus ka plus e to the ka. This is going to be equal to, now we factor out a e to the minus ka, and we have 1 minus 2m alpha h bar squared k, and this is our second equation. So the first one is this right here. Just as we did before, I'm going to put them together in the next slide so it's easier to solve. So this is our equation number 1. Okay, so, and now 1 and 2, we want to determine the, at least see if there are any bound states, how many there are. So let's see. We can now, just as before, replace this a e to the minus ka by this right there. So I'm going to copy it so I don't have to write it again. Then we have this part right here. Okay, I did not calculate the space correctly. Okay, and now we have to multiply by this. Okay, so now we just want to multiply through. So we can cancel out the c's. So we get on the left hand side e to the minus ka plus e to the ka. This is going to be equal, and now we just multiply as we did before, e to the minus ka minus e to the minus ka factor of 2m alpha h bar squared k minus e to the ka plus 2m alpha h bar squared k e to the ka. Okay, so now once again, let's see, this cancels out this right over here. We can add this to the left hand side, so we get 2e to the ka, but now we have another e to the ka right here, so we can actually put that one on the left hand side as well and just factor out the e to the ka. So we get 2 minus 2m alpha h bar squared k factor of e to the ka, and this is just going to be equal to minus e to the minus ka, which is this last term right here, factor of 2m alpha h bar squared k. So the first thing we can do here is just divide everything by 2. We just get rid of this. So there we go, and now we can multiply by e to the minus ka. So we get rid of this exponential right here, and this will turn into minus 2ka. And as before, we can also multiply, well, let us also do that in the next slide. So we have a bit more breathing room. So we can now multiply by the inverse of this right here. So basically by h bar squared k m alpha. So here we're going to get h bar squared k m alpha minus 1. This is going to be equal to minus e to the minus 2ka. But now we have this minus sign here. We could in theory leave it like this, but I prefer to write it the other way around. So just multiply by everything by minus 1. So we get this here negative and this here positive. So this is now the transcendental equation that we need to solve in order to determine how many bound states there are when we have odd solutions. So we're going to get these functions of k once again. So let's graph them. So this exponential is actually the same as before. So we know what happens. It begins at 1, doesn't really touch 0, so this 1, but it decays exponentially from there. But now this right here, when k is very close to 1, it's actually going to be here at 1, 2, but we have to take into consideration these functions do not actually go to 1, right, when k is 0, because k does not go to 0, so these functions will not go to the value 1. So that means that 1 is not a solution. That's very important. So, and then the form of this is going to depend on what exactly this alpha is going to be. So we might get a very, very weak alpha. For some values of alpha, sorry, this is going to be basically a horizontal line. So it might actually not have solutions. That's different from what we had in the even case. In the even case, regardless of the value of alpha, you are always going to have a solution. In this case, that's not the case. If this part right here, if the slope is very, very small, then there just might not be a solution at all. And depending if it is somewhat greater, then you might actually have a solution. So that is interesting. The bound states for odd solutions do not always exist. They do need the alpha to satisfy certain conditions. So that is quite interesting. So that is actually the answer to this question. In order to determine exactly what the energy levels would be, because remember the energy is inside of k, we just have to write what k is. But for that you need some specific value of alpha, and then to apply some numerical methods or graphical methods or however you want to solve that. But at least for us this is going to be good enough. It's also usually what teachers ask in the exams. But if you are interested, you can by all means just go ahead and give alpha some value. So, and there is one last part. It is they ask us to sketch the wave functions. So that means sketch the odd and the even solutions. So let's just go ahead and do that quickly. So this is going to be our potential of x. We know that the potentials have this shape right here. Well, I guess in this case we are going to be shaping the wave functions, right? So let's write it like that, and let's just put here the potentials for reference. So this is going to be minus a, and I'm going to copy this for the case of the odd solutions. So this is going to be even, and this is going to be odd. So for even solutions, remember you can just go back and see the wave function. The wave function decays when it goes to infinity, to minus infinity, and when it goes to infinity. Okay, like that. Up to a is right about here. And then, well, this is not very symmetrical, but it is just a sketch. And then in this region, as we saw before, it's going to decay up to a minimum and then go back up. So, well, this is not very symmetrical, but it is supposed to be symmetrical. It is exactly the same, and you can actually see that this is going to be symmetric with respect to the y-axis, at least to this vertical axis. And in the case for the odd, in this odd functions, now one of those, remember, we have a equal to minus f. So that means that when for example, we have a wave function decaying like this, the other one will be in this other region. And in between, we need this to also be odd, right? In this region number 2, we need it to be an odd function. In this case, it is even between the two regions as well. In this case, it is obviously odd. So this is what these wave functions look like. In this case, you could obviously invert these to the sign here, but it is still going to be odd. So that is the solution to this problem, and I hope you can see that using this trick made it a lot easier. The video is quite long anyways, but it is mainly because I was explaining it, but you can see that it really saves you a lot of algebra, and in fact we get basically using these conditions, we get the end result from applying those border conditions in the previous video. So I hope you enjoyed it, and I will see you in the next video.